Okay, sorry about that. So previous video got cut off after a certain point. And that's not where I wanted to stop it, but that's okay. We'll keep moving on. So on to number 2, where we have the function g of x equal to 1/3 raised to the x power. So again, we're going to make ourselves an xy table. Pick a few different input values. Okay, so again, -2, -1, 0, 1, and 2. And we're going to find the outputs that correspond to those inputs. Okay, so when we plug -2 in the place of x in our function, 1/3 to the -2 power is 9, 1/3 to the -1 power is 3, 1/3 to the 0 power is 1, 1/3 to the first power is 1/3, and 1/3 quantity squared is 1/9. So we're going to take those same 5 points, well, not the same 5 points, but we're going to take those 5 points and plot those in the coordinate plane. So we have -2, 9, -1, 3, 0, 1, 1, 1/3, 2, 1/9. Okay, so our curve looks like so for the function g of x. And when we compare those two graphs, it looks like f and g are y-axis reflections of one another. And that is the case because if we think about 1/3 raised to the x power, I can rewrite 1/3 as 3 to the -1 power raised to the x power. And then when I have a power raised to a power, that's like saying 3 to the -x power. Well, if I compare the graph of 3 to the x power on the left with 3 to the -x power on the right, if we take the opposite of the x value for a function, that corresponds to a y-axis reflection, which is what is demonstrated by those two graphs. Okay, so what we're going to do is we're going to take the graphs of those two functions and use them to generalize some properties of exponential functions. So on the left, we have properties of the function f of x equal to a raised to the x power. So the exponential function a raised to the x power, where our base a is bigger than 1. So I'm going to use the graph on the left to generalize the properties on the left. And then we're going to use the graph on the right to generalize properties of the exponential function f of x equal to a raised to the x power, where your base a is some fraction between 0 and 1. Okay, so let's run through these properties really quickly. We'll do them entirely for bases a that are bigger than 1, and then we'll do it entirely for bases a that are fractions between 0 and 1. So domain, when we look at the domain of our graph on the left, it's all real numbers. So I'm going to go ahead and write that in interval notation as the open interval from -infinity to infinity. If we want the range of the function on the left, looks like the y values are bigger than 0. So we're going to write that as the open interval from 0 to infinity. Our x-intercept, there is no x-intercept, so that graph is never going to touch or cross the x-axis. The y-intercept takes place at the point 0, 1. Okay, so property 3, when we look at the graph on the left, it has an asymptote. It has a horizontal asymptote at y is equal to 0, which is the x-axis, so the graph approaches the horizontal asymptote as the x values go to -infinity. So as x, that arrow is going to mean like approaches or goes to -infinity. Okay, property number 4 is that this function is increasing and 1-to-1. So it's an increasing and one-to-one function. So I know it's increasing because as I move from left to right on that graph is moving in the upward direction. I know the function is one-to-one because that function passes the horizontal line test. So a horizontal line is only going to intersect that graph in one point. The significance of that function being one-to-one, hopefully you guys remember this from the previous lesson, is that the inverse is going to be a function. And that's going to be like really important for us in the next lesson. And as we move through this unit, exponential functions have inverses that are functions. And we're going to see in the next lesson that the inverse of an exponential function is a logarithmic function. Okay, the graph is continuous for property 5, which means that you can draw that graph without lifting your writing utensil. When we get into pre-calculus next year and into calculus the following year, we'll talk more about what it means for a graph to be continuous. Okay, and then lastly, the graph of an exponential function is always going to contain 3 points. So when I input -1, a to the -1 power gives me an output of 1 over a. When I input 0 into the function, a to the 0 power gives me an output of 1. And when we input 1 into the function, a to the first power gives me an output of a. Okay, now when it comes to graphing exponential functions, these 2 points here are going to be the 2 points that we graph on any exponential function. Okay, so 0, 1 and 1, a. You're going to graph those 2 points, and then if we graph using transformations, you're going to shift that graph around in the coordinate plane. Okay, so I want you to do the same thing using the graph on the right, so the graph of 1/3 raised to the x power, to generalize properties of the exponential function f of x equal to a raised to the x power, where your base a is a fraction between 0 and 1. So go ahead and pause the video to do that. And then when you're done, you can go ahead and turn the video back on to check your work. Okay, so working through this, again, the domain is all reals. So I'm going to write that in interval notation as the open interval from -infinity to infinity. The range, once again, is y is greater than 0. So that's the open interval from 0 to infinity. There are no x-intercepts, so this is none. Y-intercept still occurs at the point 0, 1. There is still a horizontal asymptote at y is equal to 0, which is the x-axis. But this time, the graph approaches the horizontal asymptote as the x values approach or get closer and closer to infinity. When we look at property 4, this function is decreasing. And it's also a 1-to-1 function. The graph is continuous. And once again, when I input those 3 x values, when I input -1, a to the -1 power is 1 over a. When I input 0, a to the 0 power is 1. And when we input 1, a to the first power is a. Okay, so we get the same 3 points on the graph of our curve. Okay. Again, when we graph these, we are going to just take these 2 points here, 0, 1, and 1, the base, and then use transformations to shift our graph around. Okay, so let's get into an example illustrating graphing exponential functions using transformations. So the directions here ask us to graph the function f of x equal to 2 raised to the power of 1 minus x plus 2, and determine the domain, range, and asymptote. Okay, so we're going to start with our base function here. So 2 raised to the x power. So if we want to graph any exponential function, again, the 2 points on our graph are 0, 1, and then 1, the base, which in this case is 2. And we're going to draw our exponential curve passing through those 2 points. So when we shift our graph around, you have to clearly mark where these 2 points here are located. Okay, so next function, if we're going to perform our transformations in order, if there is a horizontal shift to be performed, which there is here, we have to perform the horizontal shift first. Okay, so the next function we want to graph is 2 raised to the x plus 1 power. So if we add 1 inside the function, that's going to correspond to shifting the graph 1 unit to the left. So we're just going to take our 2 points at 0, 1 and 1, comma 2 and shift those 1 unit to the left. So that's now at negative 1, 1 and 0, comma 2. Okay, so graphically, our curve looks like so. We know the vertical shift we perform last, so the next transformation we want to perform is we want to take the opposite of the x value. Okay, so when we take the opposite of the x value, that's going to take our entire graph and reflect it across the y-axis. So when we reflect across the y-axis, we are taking the opposite of the x coordinate of every point. Okay, which the point that is at 0, 2 is going to stay at 0, 2, but the point that was at negative 1, 1 now gets shifted to 1, comma 1. Okay, so graphically our curve looks like so. And then the last thing we're going to do is add 2 to our function. So that's the function f of x equal to 2 raised to the 1 minus x power plus 2. So we know that our graph is going to get shifted up 2 units. Now, there is a feature on our graph that we've known has been present the entire time, but we've never technically marked it yet. And that is the horizontal asymptote at y is equal to 0. So if we shift our graph up 2 units, the horizontal asymptote gets moved to y is equal to 2. And then the 2 points on our graph, the first point, which was at 0, 2, gets moved to 0, 4. And the second point that was at 1, comma 1 is now at 1, comma 3. Okay, so graphically our curve looks like that. So again, you need to clearly mark the location of our 2 starting points. That's what I'm going to be looking for, and then your graph having the correct shape. Okay, so domain for this function is all reals. The range is going to be the interval from 2 to infinity, and then we have a horizontal asymptote at y is equal to 2. Okay, so that's sketching the graph of that function using transformations and then identifying the domain, range, and horizontal asymptote. Okay, so we're going to transition now into looking at the most important exponent base that we're going to deal with in math moving forward. Okay, so the most important exponent base is the exponent base e. So we're going to talk about how we come up with the value of e, and then we'll take a look at graphing exponential functions with base e. Okay, so we said that the number, or we say that the number e is defined as the number that the expression 1 plus 1 over n raised to the n power approaches as n approaches infinity. Okay, so what we want to do is we want to find an approximate numeric value for e. You guys need to get a calculator out to do this. And what I've done here is I've constructed a table with 2 columns. So the first column is for values of n, and the second column is for values of 1 plus 1 over n raised to the n power. Okay, now I'm going to have you guys complete this on your calculator. and then I want you to round the results to 6 decimal places. So when we plug 1 in, we get 1 plus 1 over 1, which is 1 plus 1, which is 2, raised to the first power. So that expression when n is equal to 1 is equivalent to 2. That's the only one that we can do by hand. The rest you're going to need the calculator for. So you're going to do this when n is 10, when n is 1,000, when n is 1,000,000, and when n is 1,000,000,000. Okay, so what you should have come up with, when n was 10, I got 2.593742. When n was 1,000, I got 2.716924. When n was 1,000,000, I got 2.718280. And when n is 1,000,000,000, I got 2.718282. Okay, so that means that the numeric value of e, so in math, we typically round to 3 decimal places. So e is approximately 2.718. Now, so if you're going to do a calculation with e in the future, you're not going to want to put like 2.718 in the place of e. There's an actual e button on your calculator that you're going to want to use if you're doing computations involving the number e. Okay, so let's do a quick graph of the function f of x equal to e raised to the x power. Okay, so we said that, again, anytime we graph an exponential function, the 2 points on the graph of the exponential function are 0, 1, and then 1 comma the base, which is e. So we're going to say, like, for graphing purposes, e is going to be like 2.7. So you just want to eyeball where 2.7 is on your graph. So the graph is going to contain the point 0, 1, and then 1 comma 2.7. So roughly, the graph of your curve is going to look like so. Okay, so we'll stop there, and then I'll pick the next video up from that point.